This video covers the basics of simulation. Simulation will be used for several purposes during this class, but at the beginning of the class, simulation will primarily be used to generate idealized data sets that we can use to illustrate different data analysis concepts. There are three different categories of simulation functions that we'll be talking about in this lecture, although more information can be found in the previous lectures about simulation for the Computing for Data Analysis class. The first class of functions generates random variables from a particular distribution. These functions start with R, followed by a set of letters corresponding to each distribution. You can type question mark followed by any of these functions to see which distribution the data are generated from. Similarly, for densities, the functions start with D, followed by the same representative letters for each distribution. Again, you can type question mark followed by any of these functions to see which density this particular function will produce. We will also cover sampling, both with replacement and without replacement, in these lectures. First, we're going to talk about the R functions. So here I say R foo, where foo represents the letters for a particular distribution that you care about. So, if you look at the arguments of R norm, there's three arguments: n, a mean argument, and a standard deviation argument. N is the number of variables that you'd like to have produced, and these are the parameters of the distribution. So if you want to generate 10 heights with a mean of 188 and a standard deviation of 3, you would use this command. If you type heights, you will see 10 randomly generated heights. You can do a similar thing with a binomial distribution. Here the arguments are n, size, and probability. Remember that the binomial distribution is equivalent to flipping a certain number of coins with a specified probability. Here we can generate 10 different scenarios where each time 10 different coins are flipped, each of those coins being fair, and the number of heads is added up. So for example, here 10 coins were flipped and 3 came up heads. Then 10 coins were flipped and 4 came up heads, and so forth. In this way, you can quickly generate lots of data to look at and use as idealized data sets for evaluating data analyses. Similarly, you might want to be able to generate values of a density. The reason why is you might want to be able to make calculations about the probabilities of x values being in particular ranges or other random variables being in other ranges. So recall that for a normal distribution there are two parameters, the mean and the variance, and a normal 0,1 density function looks something like this. To generate the values of this density, we can use the dnorm function. The arguments of the dnorm function are x, the value where we're going to calculate the density, the mean, the standard deviation, and whether to return the values of the density in log units. First, we can generate a set of x values that's a sequence from -5 to 5 of length 10, where the values are equally spread out between -5 and 5. Then we can apply the dnorm function to calculate the normal density at those points. Here we pass the parameters mean equals 0 and standard deviation equals to 1. We can then report the values of the normal density at each of those x values. Here I've rounded the values to 2 significant digits to make it easier to see. So you can see that for values of -5 and 5, the density values are very low, which corresponds to the picture that we saw on the previous slide. For values near 0, the density is much higher, which also corresponds to the picture. We can also calculate the density functions for discrete random variables like the binomial distribution. Remember, if we let x be a random variable that's binomial with n equal to 10 and p equal to 0.5, this is equivalent to considering a random variable that is the number of heads that occur when 10 coins are flipped and all those coins are fair. Recall that the expected value is 5. We expect to see 5 flipped head coins. To calculate values of the binomial density, we can use the dbinom function. This has parameters x, size, prob, and again, whether we should return the probabilities on the log scale. Now we can generate a set of x values that goes from 0 to 10 by 1, so that's all the values from 0 to 10, and we can calculate the binomial density at all of those values. We are going to calculate the binomial density for coin flipping where you flip 10 coins and each of them is fair. So in each case, we are generating 10 random flips of the coin and getting a certain number of heads. We can calculate that binomial density, again, using the directly, or we can round the values again so that they're easy to see. Flipping 0 heads out of 10 coin flips when the coin is fair is again a very unlikely proposition, as is flipping all 10 heads. Meanwhile, values near the center, centering on 5 values, are much higher values of the density. In addition to generating random variables and drawing density functions, we can actually sample from variables that we've already generated. So we're going to look at the sample function. This function has arguments x, which is a vector of values, size, which is the number of random samples that we'd like to take, whether to sample with replacement, which I'll explain in a second, and which probabilities to use when sampling the values. So for example, I can generate 10 heights with the rnorm function with mean 188 and standard deviation of 3. If I sample those heights with replacement, some of the heights values that get sampled are the same value. Because how sample works is it draws one random value from the vector of heights, then replaces that value in the vector of heights, and then draws a new random sample from amongst all 10 values. So here you see the value of 188.2 repeated 1, 2, 3 times. You can also sample without replacement. So for example, if we have the same vector of heights, here they are, we can sample again a size 10 random sample from that vector of heights, now replacing false. What this means is, first, a random sample is drawn from the heights vector, then that value is removed from the heights vector, then a random sample is drawn from the remaining values, and so forth. It turns out, since heights is a vector of length 10, and we've taken a sample of size 10, you actually end up with the exact same values as you started with, but in a permuted order. You cannot take a sample of size greater than the length of the vector if you are not replacing the values. You can also sample according to a set of probabilities. So for example, if we let the heights be this same vector, we can now assign probabilities that each particular value is sampled. So we can assign the probabilities in this way. There's a 0.4 probability that the first value is sampled, a 0.3 probability the second value is sampled, a 0.2 probability the third value is sampled, a 0.1 value the fourth probability is sampled, and 0 probability any of the remaining values are sampled. The sum of these probabilities must equal 1. So if we sample the heights vector, replacing the values with these probabilities, we see that the last value is never represented in our random sample. That's because we assigned the probability of it being sampled to be equal to 0. At the same time, we see that the first value, 187.2, is represented several times since its probability of being selected is relatively high. This allows us to sample under different schemes using the sample function. Often when generating a set of random numbers, you will want to be able to generate that same set of random numbers to be able to illustrate the point that you are focusing on when you pass the script off to someone else. The way to do that is by setting the seed, and you can do that through the set.seed function. The set.seed function has one argument, which is a single integer. You pass it that integer, and then you run a function that either generates random variables like rnorm, or that samples from a set of random variables like sample. As long as you set the seed and generate variables in the same order, you will get the same values out. For example, if you set the seed to be 1, 2, 3, 4, 5, and generate 5 normal random variables with mean 0 and standard deviation 1, you get these 5 values. If you set the seed again and generate 5 normal random variables again, you again get 5 variables of the same values. An important thing to keep in mind is that you need to keep the order in which you generate or sample variables the same in order to get the exact same results out. For more information on distributions, you can go to the index of distributions from R at this website here. You can also learn more about simulation in R in the Computing for Data Analysis video that's available from YouTube or as background material for the course from the course website.